This video is devoted to the aeroelastic phenomena in the pseudo-static approximation. This approximation is a little weaker than the quasi-static approximation, for which the solid was considered non-moving with respect to the velocity of the fluid. This time, we will consider that it has a constant velocity. In a previous video, we showed this by looking at the derivative with respect to time of the kinematic condition. We have indeed shown that if UR squared is large compared to the displacement number, then this condition becomes du on dt equals 0. The fluid mechanics problem does depend on the position of the interface and the velocity. If we transfer this to an oscillator equation describing the dynamics of the structure according to a mode, and we scale this, we obtain a force equal to the product of the Cauchy number and the fluid stress projected on the mode. In view of the preceding discussion, this projected stress is in this approximation framework a function of Q and Q dot. Let's see this in the case of a profile with any shape in a flow at velocity u0 animated by a solid body motion. The eigenmode is defined by a unit vector denoted I. The motion is therefore a product of the modal displacement Q and I. In dimensionless form, it is the same thing. In this analysis, we will place ourselves in the frame of reference of the solid in motion. The corrected velocity vector is noted v and it is u0 minus q dot I. In dimensionless form, we find for small v ex minus I q dot on ur. First of all, let us consider an oscillation in the direction of the flow. I is thus ex. The relative velocity is therefore also directed along ex and is u0 minus q dot. In dimensionless form, this gives 1 minus q dot on ur. If the solid is stationary, the fluid force is equal to 1/2 of rho u0 squared times the drag coefficient. We call that this coefficient is a function of the Reynolds number. In dimensionless form, the fluid force is equal to 1/2 of CD. If we take into account the velocity of the solid, the coefficient depends on the apparent velocity v and on the drag coefficient for the apparent Reynolds number based on the velocity v. Without dimension, this is written as 1/2 of the apparent velocity squared times the drag coefficient. The apparent Reynolds number is written rho VL on mu, which with dimensionless quantities is written as the product of the Reynolds number by 1 minus q dot on ur. We can then introduce this apparent Reynolds number into the expression of the fluid force, and we obtain an expression where appear the velocity q dot, the reduced velocity, and the drag coefficient, which is a function of the apparent Reynolds number. This force is a nonlinear function of q dot, which we will now linearize. Let's do a Taylor expansion of the force from the value q dot equals 0. Keeping only the linear terms at q dot, we find this expression where it should be noted that to obtain it, we have considered that d on dq dot is equal to the derivative of the Reynolds number with respect to q dot times the derivative with respect to the Reynolds number. We obtain the fluid force for q dot equals 0 plus two other terms proportional to q dot. These last two terms lead us to define an added damping which depend on the evolution of the drag coefficient with the Reynolds number. Let's see what this gives for the particular case of a circular section whose drag coefficient was described in a video on aerodynamics. Throughout the range of Reynolds number represented, there is a range of values where the negative slope is large enough that the damping coefficient can be negative. This is the range of values where the drag crisis occurs. It is easy to understand what positive damping does to the dynamics of a structure. The energy dissipation leads to oscillations whose amplitude decreases with time. On the contrary, a negative damping leads to oscillations whose amplitude increases exponentially with time. We have just identified a phenomenon of dynamic instability. This instability is called instability by drag crisis. It can be observed in the field of offshore oil and gas or offshore wind. Anchor cables, power cables, or umbilicals are subject to currents and can sometimes be in the Reynolds number range where the drag crisis occurs. We will now look at the motion of the structure in the direction perpendicular to the flow. I is now equal to EY. Let's place the solid at a given instant of the oscillation. The instantaneous velocity is noted q dot, directed along EY. If we place ourselves in the reference frame of the solid in motion, we have a solid with zero velocity in a flow with velocity v, which makes an angle alpha with the main direction of the flow. This angle of attack is the arctangent of minus q dot on u naught. This writes arctangent of minus q dot on ur with dimensionless parameters and can be approximated as minus q dot on ur for small motions. The square of the apparent velocity is simply the sum of the squares, giving a dimensionless apparent velocity equal to square root of 1 plus q dot squared on ur squared. It can be approximated to 1. The motion of the solid perpendicular to the flow therefore induces a change of angle of attack without change of apparent velocity. Let's rewrite the value of this apparent angle in the upper left corner. We will now study the forces exerted on this profile. The fluid force is noted F. What we know are the aerodynamic coefficients, lift and drag, as function of alpha. What we are looking for is the force Fy projected on the y-axis. Given the rotation alpha between these two sets of axes, we obtain Fl cosine alpha plus Fd sinus alpha. In dimensionless form, the fluid force is 1/2 of Cl cosine alpha plus 1/2 of Cd sine alpha. We then perform a Taylor expansion to order 1 in alpha of this force. The terms in sine alpha can be neglected compared to the terms in cosine alpha. And cosine alpha can be approximated by 1. By replacing alpha with the expression found earlier, we finally find the linear component of this fluid force. Let's give mass, stiffness, and damping to this profile. The system behaves like a damped oscillator with a force at the right-hand side coming from the fluid. In dimensionless form, this is written q dot dot plus c times q dot plus q equals Cauchy times F. If we expand F, we can put on the left side the force proportional to q dot, making an added damping appear. We can then represent the evolution of this added damping coefficient as a function of Cauchy on ur. Noting that Cauchy is proportional to the velocity squared and ur proportional to the velocity, this is equivalent to varying u naught. For zero velocity, the damping is c. If we increase the velocity of the flow, the total damping increases when dCl over d alpha is positive, and decreases in the opposite case. The total damping of the system can then become negative and consequently lead to a flutter instability, which is usually called galloping. We can now ask ourselves when this instability can occur. We will look at this in the case of the NACA 0012 profile. The first thing to note is that the drag coefficient is always positive. Next, for low angle of attack, the derivative of the lift coefficient with respect to the angle of attack is positive, which leads to a positive damping. On the other hand, at higher angles of attack, the lift drops. This is the phenomenon of stall or lift crisis. In this case, the added damping can be negative, which can make the total damping negative if the velocity is high enough. We are dealing with an instability by lift crisis. This instability can be demonstrated simply in a wind tunnel. You have here a wing profile mounted on two very long flexible bars. If the bars are long enough, the rotation can be neglected, and we are dealing with a system equivalent to our mass spring system. At low incidence, it is easy to see that the damping is positive. If the system is moved from its equilibrium position and then released, we have an oscillation of decreasing amplitude. On the other end, for larger angle of attack, stall occurs, and the negative damping leads to oscillation of increasing amplitude. Even if the system has an equilibrium position, it is unstable and the slight disturbance is amplified in time. To finish with this instability, other profiles can be studied. And instability can occur whenever the derivative of the lift coefficient is negative. As we have seen previously, for some profiles, this can depend on the Reynolds number or even on the level of turbulence present in the flow. In conclusion of this video, we have discussed the pseudo-static approach, which allowed us to highlight added damping. Thanks to the implemented approach, the damping is only a function of the properties of the lift and drag coefficient of the studied profiles. The damping responsible for the drag crisis is related to the evolution of the drag coefficient with the Reynolds number. The damping responsible for the lift crisis depends on the drag coefficient and the variation of the lift coefficient with the angle of attack. And finally, we see that this damping varies as Cauchy on U are. They are hence proportional to rho u. The denser the fluid and the higher the velocity, the greater the damping.